Hey everyone. So today we're starting the final unit in this class, which is the unit on rotational motion. There are a lot of sort of new concepts and new ideas that turn up in this unit, and today I'm just going to talk about one or two of them. All right, so to set this up, let's say I have something kind of like a bicycle wheel. It has a radius of 40 centimeters. And let's say on one of the spokes on this wheel, I put a marker halfway out from the center, let's call it A, and then I put another marker, B, all the way out on the edge of the wheel. And then I start to rotate this wheel around. Now I could ask you, which of these two marks, A or B, has the higher speed or greater velocity? Well, it turns out there are actually two different types of speeds that we can talk about here, and the answer to that question turns out to depend on which one we're talking about. All right, so let's start to look at this question. Let's say we rotate this thing around so that it makes one revolution in 10 seconds. So say 10 seconds per revolution here. All right, so what is the speed of particle A and particle B? Well, one way we know to calculate speed, from the definition, speed is just distance traveled divided by time. All right, so for A, the speed, which we'll use the letter V to represent that as usual. Use that for velocity or speed. Well, I'll kind of use them interchangeably in this video. So what's the distance traveled per time? Well, let's look at exactly one revolution. So what is the distance traveled in one revolution? Well, A is going to sort of trace out this circular path here that has a radius of 20 centimeters. I drew that really off-center, but you get the idea. So what is the circumference of that circle? Well, the circumference of a circle is 2 pi times the radius. So that'll be 2 pi times the radius, which is 0.2 meters. And I divide that by the time, which we said was 10 seconds per one revolution. All right, so if we multiply all that out, we get a speed of 0.126 meters per second. All right, so what about B? Let's call this VA, just so we're clear. B, I'll call that speed VB. So we're going to calculate that in a similar way. B is going to go all the way around the outside of the circle. The circumference of that circle will be 2 pi times the radius, which is 0.4 meters this time. And that goes around in the same 10 seconds as A. So if we multiply this out, we get 0.251 meters per second. And notice that's double the speed of A. So it seems that B has a greater speed than A. And this is what we call the linear speed. All right, well, there's one other way we can think about the speed of these objects, and that's just how many rotations do they make every second. So these two objects are going to both rotate in the same amount of time. So that seems like an important thing as well. Maybe it's significant that they both, rotate through the same angle in the same time. So how could we quantify that? So let's define a different type of speed here. Let's call it angular speed. So speed was distance traveled divided by time. Angular speed is going to be an angle traveled divided by time. All right, so what is the angle that is swept out by these particles in a unit of time? Well, in 10 seconds, these objects rotate through 360 degrees. All right, so we need a new letter, first of all, to represent this. We're already using V to represent linear speed. We don't want to use that for angular speed because that will get confusing. So I'm going to use this symbol here. So this looks like a curly W. This is a Greek letter called omega. So a lowercase omega if you're curious. So the angular speed for A would be 360 degrees per 10 seconds, but we're actually going to use a different unit here. I'm going to use a unit called radians, which some of you may have heard of. And for those of you who haven't, a radian is just another way of measuring an angle. And the conversion there is that 360 degrees, let me write this in black, 360 degrees is equal to 2 pi radians. And we'll maybe see a little bit about why this is important or useful in just a minute. All right, so the angular velocity of B, that's going to be the exact same, right? It rotates through the same angle in the same amount of time. So we can use rad as short for radians. So that's going to be also 2 pi radians over 10 seconds. So I guess we could go ahead and multiply that out. It's going to be 0.628 radians per second. All right, so let's look at the two equations I've written in blue. The calculation for linear speed is 2 pi times the radius of the circle divided by the time. The calculation for the angular speed is just 2 pi divided by the time. Those two equations are almost identical. The only difference is that if we want to calculate the linear speed, we have to add an extra number in the numerator, which is equal to the radius. So the linear speed and angular speed of the same object are actually very closely related if we use radians rather than degrees. So this is the reason we use radians in physics. So if I want to relate these two equations, I can say the linear speed of B is just the angular speed, 2 pi divided by 10, and then I have to multiply by the radius. So I'll call it RB because B and A have different radii. So this, we can make it more general. V equals omega times R. This is the relationship between linear and angular velocity. Whoa. All right, so if we're looking at this example, if we have something like this where these two particles are sort of both attached to a fixed platform or object that's rotating, they may have the same angular speed, but if they're different distances from the center, then the one with a larger radius, the one that's farther from the center, is going to have a greater linear speed. So you see in this example, A and B both have the same angular speed because they both go through one rotation in the same amount of time, but since B is farther from the center, it ends up with a greater linear speed than A has. And in fact, since it's twice as far away from the center exactly, it has exactly twice the linear speed. So one last thing before I end this video, let me just talk a little bit more about this notion of a radian, in case anybody is curious about where this comes from. So you may have learned, if you've seen this in your math class, you may have learned that the number of radians in a full circle is 2 pi, but why is it 2 pi? So let's say I have a circle here with radius r, and let's say I draw two radii that are separated by some angle. We usually use the Greek letter theta to represent an angle. These two radii will cut off a part of the circle here. Now, let me color that in red. So this arc here has a length that could be measured. Now, you can imagine if we make this angle theta larger, that's going to make the length of that red arc larger as well. If we double the angle, we double the arc. The radius will also affect it as well. If we make the circle bigger and just blow it up to 2 times its size, then the arc is going to get larger as well. So the length of this arc, which let's call it d, is proportional to the radius, and it's also proportional to the angle. And let's say I happen to have this so that the length here is exactly equal to the radius. So that will happen for a particular angle, and we call that angle a radian. So this angle here would be 1 radian if d is the same as the radius of the circle. So that means we can say that d in general is equal to the radius multiplied by the angle if the angle's in radians. So if theta is equal to 1, then d and r are the same, but if theta is larger or smaller than 1, then d will be larger or smaller. But this equation only works if this is measured in radians. All right, so taking that definition, how many radians should be in a full circle? Well, let me move this over a little bit. Let's draw another circle here. So let's say we let this angle go all the way around the circle, full 360 degrees. All right, so what is this angle? Well, what is the length of this arc that I just traced in red all the way around the circle? Well, this arc is the full circumference. The circumference of a circle is equal to 2 pi times the radius. So if I look at that and match that to the equation over on the left, d equals r times some angle in radians, then this part here must be the number of radians in a full circle. So that's where we get this conversion that there are 2 pi radians in 360 degrees. It basically comes down to what the definition of a radian is, and also the definition of pi being related to the circumference of a circle. All right, so we will be using radians rather than degrees in this class. So you want to make sure you are familiar with that conversion, the one that I've got boxed up in the top of the screen here. So 360 degrees equals 2 pi radians. All right, so those are the main take-home parts of this video. Be familiar with these two types of speed, linear speed and angular speed. Know the relationship between those, which is boxed down here, v equals omega times r. And then just, if you're not already, be familiar with what a radian is and how many radians are in a full circle. All right, so that should do it for today. Thank you for watching.